many simulated experiments do I have to run before that distribution is about right? And the answer is it's small enough that it doesn't take very long to compute. It's big enough that it's going to be as accurate as we care about. Question is, does this all depend on everything being normally distributed? No. That's where the central limit theorem is going to come and help us. And actually, for this kind of computational approach, we don't even need the central limit theorem, which is, if the distribution of human weight was a Pareto distribution, which is one of these crazy distributions that does not have a finite mean or variance, and therefore the central limit theorem does not apply, it would nevertheless be the case that if we run this methodology, what we would get here for our sampling distribution would be probably good enough for practical purposes. We might have to crank up iters, getting back to the previous question. 1,000 might not be big enough. If I'm working with an underlying distribution that has huge variance, I might need to run lots and lots of iterations before I really see everything that might happen. So the observation is, if I'm working with a long-tail distribution and I have a relatively small sample, there's probably crazy stuff out there that I've never seen. And you're absolutely right. So now I need some kind of methodology that gets me from a sample to a long-tail model. That's actually probably a case where I would switch over to using model number 2 and put here a long-tail distribution. Yeah. So the question is, if it is Pareto or some other crazy distribution and I crank up iters, is that going to be good enough? Am I really going to... the sampling distribution in that case will not be Pareto, but it will still probably have quite heavy tails. And now it's going to become a practical question of, is it good enough? How big does iters need to be? Yeah. Bimodal distributions are mostly going to be okay. Resampling is going to handle that just fine. The central limit theorem probably will apply, so the sampling distribution will be unimodal, even if the population distribution is not. What your sampling statistic is. If you have a bimodal distribution and you are blindly computing means, you might be misleading yourself. But that's a problem with you chose the wrong sampling statistic, that's not a problem with resampling. Okay. I highly recommend that you take this diagram and have it tattooed somewhere convenient on your body. Because if you understand this, you understand resampling. Okay. The other thing that's in the notebook, if you are a fan of design patterns, what I've done in the notebook is I've used a class called resampler to represent this framework. Basically, this diagram is represented in code by the resampler class, and then your job is just to provide the little methods like sample stat and run model, and it does the whole thing. I'm not going to get into that. Again, I don't want to get too far into object-oriented programming other than to point that out. We should take a break. I'm going to make the last part of the notebook optional. If you want to work through it during the break, I'm happy to answer your questions. And when we come back, we'll get into a couple of review topics. It is 3:35. Let's come back at 3:45. A little bit of trivia for people who are old. What's the picture on the right? Anybody know what that is? That is Bill Buckner mishandling a ground ball from first base during the 1985 World Series, causing the Red Sox to not win for another 19 years. But that's not my bitterness about the Boston Red Sox is not the point of this class. So, Couple of review questions. Number one, what is the difference between a standard deviation and a standard error? Two things that people often get confused. Let me suggest a way of thinking about this, which is a standard deviation is about the population. A standard error is about your estimate. So if you're telling me a standard deviation, you're telling me about people in this case. So my example here is that the standard deviation of adult male height is 7.7 centimeters. That's telling me how much people differ from each other. If I make an estimate, and I tell you that I've estimated the adult mean height, and I think it's 178 centimeters, you ask me, how precise is that estimate? And I say, my standard error is very small. It is 0.00034 centimeters. That number is telling you about my estimate. It is not about people. And notice in this example, I've deliberately chosen, this sample size is about 300,000 people. And as a result, my standard error is extremely small, which is to say that my uncertainty due to random sampling is very, very small, which is great, up to a point. Yes, I could, but I'm not going to say that just because it's confusing. So for now, I'm just going to talk about, I'm estimating a mean, and if you ask me how good my estimate is, I will give you a standard error to tell you how good my estimate is. But the estimate could be the standard deviation, but I'm not going to say it. But you're absolutely right. We're good. Okay. So, because my standard error is so small, my confidence interval is also quite small. So notice that I actually have 5 significant digits in my measurement here, which almost never happens in reality. Now, I'm going to answer the question that I was asked a while ago, which is, what is the probability that the actual adult mean height in the U.S. population is in that confidence interval? Remembering again, the width of that confidence interval is 0.003 centimeters. What's the probability that the true value actually falls in the confidence interval? There are 2 answers to this question. One of them is a philosophical black hole. If you've studied mathematical statistics, if you've read about 20th century statistical battles, you've probably heard people say that there's a confidence interval, and the true value either falls in that interval or it doesn't. But it's meaningless to talk about probability because the true value is not a random quantity. It is unknown, but not random, and therefore it's meaningless to talk about the probability that it falls in an interval. If you like endless, pointless, philosophical debates, you can spend the next 10 years on this question, and it will embroil you in the Princeton versus Bayesian interpretations of probability, and the whole thing is a loss of wasted time. Because the probability that the true value actually falls in that range is virtually 0. Because the only thing that we've quantified is uncertainty due to random sampling. Meanwhile, we've totally ignored sampling bias, measurement error, and the other 20 things that Edward Tufte warned us about. Okay? Now, when you have a really gigantic sample size, your standard error is tiny. And what that tells you is that it's very likely that it's those other sources of error that dominate. So if you get a nice small standard error or a nice small confidence interval, you are entitled to check off your list of the 20 things that you should be worried about. You should now turn your attention to the other 19. Got it? So in this case, as I said, measurement error is likely to be a problem. You remember I mentioned those people who were 62 centimeters tall? That's hard to work with, because now, let's say that I've got someone who's 100 centimeters tall. Is that an error, or is someone actually that height? Don't know. There were a bunch of people who were like 220 centimeters tall. Error? Don't know.